we have discussed the mechanism by which the dielectric constant of an insulator becomes frequency dependent. So, we represent this by the function, the dielectric function epsilon omega. We also noted that this epsilon, since this is equal to the square of the refractive index. So, this frequency dependence also leads to a frequency dependence of the refractive index, and in particular this leads to the phenomenon of dispersion and absorption of electromagnetic waves when propagating through a medium which is characterized by this dielectric function epsilon omega. So, this is related to the real part of the dielectric constant, while absorption is related to the imaginary part, which in turn leads to absorption. So, we discussed the theory of this in a dielectric medium. Just by way of digression, we will just revert back to the case of a metal, which we have been discussing in some detail earlier, and we incidentally want to see how this behavior, this dispersive and absorptive nature is reflected in the properties of metals. Metals, as you know, are highly conducting media. So, the question is whether there will be any change, any difference in the optical behavior of metals in the response to light, because we all know it is a matter of common experience that metals are highly reflective in contrast to insulating substances which are not so. So, we would like to see whether this treatment of dispersion and absorption can lead to a detailed understanding of the optical behavior of metals. Now, one thing we know is that the metals have a very large concentration of conduction electrons, and therefore, the main properties of metal are usually understood in terms of the collective behavior of conduction electrons. In particular, one remembers that there is a phenomenon called skin effect, which is characteristic of metals, and this results in the electrons being able to penetrate the metal only up to a short distance named as skin layer or skin depth, and this depth is usually given by root of 2 by mu sigma omega. Mu is the permeability, sigma is the conductivity, and omega is the angular frequency. So, this is one thing we will keep in mind before discussing this, and going back to our discussion of the response of a free electron. Unlike the response of a bound electron in an insulator, the response of a free electron. In what way is it different from that of a bound electron in an insulator? We will see by writing the equation of motion as before, as d square x by dt square minus gamma dx by dt. This is the dissipative or resistive term. So, there was, in addition, in the case of a bound electron, there was a natural frequency of oscillation, which is in the form of a restoring force here in the equation of motion. Now, in the case of a free electron, there is no restoring force, there is no natural frequency, it is free to move under the influence of an applied electric field. So, this term is missing in the equation of motion, and we have so this is the equation of motion in the case of a free electron in a metal. Now, this gamma is the damping constant per unit mass. And we seek a solution of this differential equation in the usual way by saying that the response is also of the form of x naught e to the power I omega t with probably a phase shift, and as plugging this back we get x naught equal to and this for a small, when gamma is very small compared to 1, we can just write this as E E naught by m omega square. This will lead to a polarization in the usual way. Once we have the displacement, we can write the polarization, and that takes the form and so this leads to the frequency dependent dielectric constant. In the case of a metal, following the same procedure, we get now this term n e square by m epsilon. Let me rewrite this. So that this can be written, let n e square by m epsilon naught be called. So, this is a term which has the concentration of the electrons, the electronic charge, the mass, and the permittivity of free space. So, this is a constant which is characteristic of the metal. Now, that is taken as omega naught square, and omega naught is known as plasma frequency. Once you have that substitution, we simply arrive at a simple relation like this. And so, what does this say? So, the dielectric function of a metal has the simple form 1 minus omega naught square by omega square. So, this can be again related to the real and imaginary part of the dielectric constant, this has the form which is shown in the figure. At very low frequencies, the epsilon 1 is negative, and then it rises to 0 when omega approaches the plasma frequency, and then it goes up to the value of 1 at high frequencies. So, that is the behavior which is shown in the figure, while the next figure shows the imaginary part of the dielectric constant, which is related to the reflectivity. So, in this figure the reflectivity is plotted as a function of the wave number or the frequency. So, this shows that the reflectivity is 1 at low frequencies, which means that at low frequencies the metal reflects all the incident electromagnetic radiation, except when the frequency approaches the plasma frequency. When this behavior is explained, for omega very small compared to omega naught, there is a negative dielectric constant, and the correspondingly the refractive index, which is the square root of the dielectric constant, is purely imaginary, and an imaginary refractive index means that the electromagnetic wave is attenuated. So, it does not propagate inside the medium, inside the metal, and it is perfectly reflected, which is the reason why a metallic surface appears highly reflecting, shines. When the frequency approaches the plasma frequency, the dielectric constant approaches 0, and you have a longitudinal plasma wave which is propagated in the metal. And for higher frequencies, higher than the plasma frequency, the dielectric function change varies from 0 to 1, and this is the usual behavior in which the electromagnetic wave propagates with a phase velocity, which is given by c by root epsilon. So, that is the overall behavior, and in the case of copper, the corresponding wavelength is about 120 nanometers. This is in the ultraviolet range. That is why copper reflects visible light and appears shiny. The collective oscillations also take place in the case of positive ions in a diatomic solid, such as the alkali halides, which also give rise to plasma excitations, which are known as plasmons. But these plasmons occur at much lower frequencies, because the ion masses are much larger. It gets shifted into the infrared range. Now, we have in this treatment taken gamma as very small compared to 1 and neglected the damping term. Now, if the damping term is not neglected in the frequency dependent dielectric constant, then epsilon omega turns out to be complex, and this results again in an imaginary refractive index, which corresponds to absorption and hence attenuation of light in the medium. Because the light is attenuated, there is an energy loss, and this energy loss may equally well be described in terms of a frequency dependent conductivity. So, this is known as the AC electrical conductivity. When the incident radiation, incident wave has a time dependence. So, you have an AC response, and therefore, this is known as the AC electrical conductivity, in contrast to the DC conductivity, which we have already discussed of a metal. Now, this can be discussed again in the same formalism with which we discussed the conductivity in terms of the current density, which is NeV, and this is equal to sigma E by Ohm's law. And the equation for V, the velocity, is I omega minus gamma times V equals E E. To take into account the sign of the charge, minus Ne. So, this means that V is n E E by gamma minus I omega. So, this can be rewritten because we know that gamma is 1 by tau. We remember tau is the relaxation time for conduction of electrons. So, this can be written in terms of using this and this, we can write the sigma, the frequency dependent conductivity, as sigma naught by 1 minus I omega tau. So, that is the expression for the frequency dependent AC conductivity of a metal, and this is again displayed in the next figure, where the real and imaginary parts of the electrical conductivity of a metal is shown again as a function of frequency or wave number, and you can see the whole behavior is very different from that of the DC conductivity. Now, we turn to a discussion of the ionic polarization. We discussed so far the electronic polarization, and we now turn to a discussion of the ionic polarization. So, in simple solids like alkali halides, for example, sodium chloride, we have sodium plus and chlorine ions sitting alternately in a diatomic lattice. Now, the ionic polarization is again given by N Z E into x 1 minus x 2, where it is the relative net displacement of the two ions from their equilibrium position, or we can write x plus x minus. And again, following the same procedure, we arrive at a situation where x naught is going to the equation of motion and solving it and so on. Where this omega naught is k by mu to the power half, and mu is the reduced mass of the two ions given by from this. Once we know the displacement, we can write the ionic polarizability, and the ionic polarizability due to the displacement, relative displacements of the two ions, has the form following the same procedure which we followed up to now. Of course, we have neglected here the individual atomic polarizabilities, which are alpha plus and alpha minus. Therefore, the alpha total polarizability is this plus this plus this term. And this leads to the Clausius-Mozotti equation, which we discussed already. For the dielectric function as where alpha is given by this. and therefore, going to the different limits, you find for example, the static dielectric constant of an ionic solid setting omega equal to 0 there, that will be and we have in this omega becomes 0. So, I have whereas, the high frequency dielectric constant which we write as epsilon infinity minus 1 is got in the same way by setting omega equal to infinity there. So, the frequency dependent term goes off. So, using these two limits we can write the epsilon omega, the dielectric constant at any frequency omega. This takes the form that will be plus minus So, solving for epsilon omega we get where omega t square, this is something which one can figure out rather straightforward algebra. So, what is the meaning of all this? We have now written the frequency dependent dielectric constant at any frequency in terms of the high frequency dielectric constant and then the static dielectric constant. And a frequency which we have defined in this way. So, this helps us to visualize what is going on in terms of what are known as the longitudinal and transverse optic modes. So, we now go on to discuss the longitudinal and transverse optic modes and optic phonons. Usually they go by the contraction abbreviation Ello and TO phonons. So, in an optic mode of an ionic crystal, there is a non-vanishing polarization P, and associated with this is the electric displacement D. And when there are no free charges, we have the general relation divergence of D vanishes. Now, we apply an alternating field E equal to E naught exponential I omega t minus k x or k dot r in general. So, using this we can see div D gives rise to k dot D equal to 0, because the divergence is going to, taking the divergence means it will be replacing this by I k. So, div D equal to 0 goes to the equation k dot D equal to 0, and what is the consequence of this? This means that either D itself is 0 or D is perpendicular to k. If D is perpendicular to k, E also is and P also is. That is the significance of this condition div D equal to 0. Now, in addition, we also have for the electrostatic case the additional relation curl E equal to 0. Now, curl E equal to 0 for an oscillatory electric field again gives rise to the relation k cross E equal to 0. This means either E itself is 0 or E is perpendicular to k, no, parallel to. If E is parallel, so is D and P. So, these are the two possibilities. Now, we can discuss an Ello mode, a longitudinal optic mode. In an Ello mode, what happens? It is defined by the polarization being parallel to k. So, if P is parallel to k, naturally this condition is ruled out, therefore, only we have T equal to 0. And therefore, E is minus P by epsilon naught. Whereas, for a TO mode, P is perpendicular to k, which means that P is parallel to k, therefore, E is 0. So, this is the main difference between an Ello mode and a TO mode. Therefore, we have the frequency of the Ello mode corresponds to epsilon equal to 0, and that means omega L square, plugging back into the expression for the Ello mode, omega L square is epsilon naught by epsilon infinity into omega t square. So, this very interesting relation between a frequency of an Ello mode and the frequency of a TO mode goes by a special name, Lydane-Sachs-Teller relation. This can be experimentally verified, because one can measure the static dielectric constant, the high frequency dielectric constant, the frequency, angular frequencies of the Ello and TO modes. Therefore, one can check this relationship. Now, this in general gives back omega L is usually greater than omega T. So, the frequency dependent dielectric constant, its variation for an ionic crystal is shown in the next figure, and one can see that in the frequency range between omega L and omega T, there is again a negative dielectric constant, and the ionic crystal is highly reflective. So, no radiation can propagate in the crystal in this frequency region lying between the transverse and longitudinal optical modes. Now, we can also solve for the dispersion relationship for the transverse electromagnetic modes, and this gives a dispersion relationship when solved gives you a behavior like this. So, the dispersion relationship has two branches, one lying below omega T and another lying above omega L. So, you have in the region there are linear regions, one mode is clearly photon like and one is clearly optical phonon like. So, this excitation is known as polaritons. At very low frequencies, we see omega goes as linear and it levels off to omega T, and at high frequencies above the other branch, you have again a linear region. At very low frequencies, it levels off to omega T, and again you have at high frequencies, you have a linear region again, it levels off asymptotically to the longitudinal optical. So, in the region between omega, in this frequency range, you have highly reflective behavior and the EM waves are reflected from the surface of the crystal. So, you after many reflections, only the component of radiation with frequencies very close to omega T will survive. So, you can have a surviving radiation which is known as reststrol, or in English this is a German term which means residual rays. So, you can have a very precise way to measure the transverse optic mode frequency and also to produce monochromatic radiation close to omega T, which lies in the infrared. So, these are some applications of this behavior. We now close this with a discussion, brief discussion of a very remarkable kind of substances known as piezoelectrics. In general, all dielectric materials, when you subject it to an external electric field of sufficiently large magnitude, undergo a small change in dimension. So, there is a strain generated which is proportional to the square of the electric field at high enough fields. So, this effect is known as electrostriction, and this is observed in all dielectric materials at high enough electric fields. But piezoelectrics is different. This is one special class of dielectrics where there is a significant change in dimension when subjected to an electric field, but in a piezoelectric the strain is proportional to the field, amplitude of the field. So, the strain depending on whether what is the polarity of the field, you can have a compressive or extensive strain. So, this is piezoelectric effect. Now, usually the piezoelectric effect masks the electrostrictive effect. Now, you have not only a direct piezoelectric effect, but also a indirect or reverse piezoelectric effect, in which you have a field resulting, an electric field resulting from an applied strain. Jacques and Pierre Curie first observed this effect in 1880, and piezo means pressure. So, that is the reason for the terminology. Now, this is the interest from this comes because of the applications applied to generation of ultrasonic waves. Because of the strain waves used in sonar, and then you can also have pressure or strain sensors based on the reverse, direct or reverse piezoelectric effect. You can also have actuators, piezoelectric actuators. So, usually materials belonging to crystal classes which possess a center of symmetry do not exhibit a piezoelectric effect because of the linearity. So, it is only the non-centrosymmetric crystals which produce the piezoelectric effect. Now, that is shown in the next couple of figures, the direct and the indirect piezoelectric effect. And usually we have already discussed ferroelectrics. All ferroelectrics display piezoelectric effect. Now, in the case of a ferroelectric material, the important characteristic is that there exists a spontaneous polarization. Which can be reversed by applying the external electric field. So, a ferroelectric material exhibits piezoelectric effect only when it is polarized in this way, that is, when it is made to possess the remnant polarization. The polarizing process is called poling of the ferroelectric. Now, what are the materials? Typical examples. One of the materials which is very well known, a piezoelectric material, is quartz. Quartz is just a form of silicon dioxide, and it is usually piezoelectric, but not ferroelectric. Can be used in the form of a single crystal, and when you have a quartz crystal, this is used very often in frequency stabilization of oscillators. A piezoelectric quartz crystal of appropriate cut gives you frequency stabilization. This figure shows a single crystal of quartz in which the different cuts which are employed for production of piezoelectric slices of with the different frequencies are shown in the figure. Now, the reference frequencies can lie in the kilohertz or megahertz ranges, depending on the direction of cut and the thickness of the crystal. So, that is how the quartz is used in an oscillator. The next material is barium titanate. We have already discussed this material. It becomes a ferroelectric at 420 degrees Celsius and has a high dielectric constant, exhibits a very sensitive piezoelectric. Another one is lead zirconate. Well, it is lead zirconate titanate. it is known as PZT in short. So, this is the most widely used piezoelectric ceramic for transducer applications. Now, it is also used in the polycrystalline form. So, it has an advantage of easy fabrication. That is a crystal structure of lead zirconate titanate, and this is the most widely used piezoelectric material.